right. We are continuing with linear algebra today because that's what's happening. Check this out, though. Bam. AX equals B. My hand does kind of block it. I think it'll be okay. So, so I got the tripod on the table this time. Wait, okay. All right. So, this section is actually an extremely short section, so we should be able to just breeze through the notes and just get right into the exercises. Basically, this whole section is just about this whole section is about invertible matrices, but particularly it's tying together so much of what came in chapter 1. Oh yeah. Because it basically, and that's the thing about linear algebra. There's about 1,000 ways to say the same thing in linear algebra, is what I've sort of come to conclude. So I don't know if I want to write all these down, but I will definitely read these out. So these are all exactly the same thing. If A is an invertible matrix, then it's row equivalent to the identity. It has n pivots. The homogeneous solution only has the trivial solution. The homogeneous equation of AX equal to 0 only has the trivial solution. The columns of A are linearly independent. Oh, and it's important that A is square, because otherwise these are not all equivalent. So A columns are linearly independent. Now F is interesting because F, the linear transformation is 1-to-1. F is interesting to me. The linear transformation is 1-to-1. So that means that if A is square and 1-to-1, that means it implies in some way number I that it's also onto. I mean, these are all the same, so A is also invertible. Okay, wait, let's just read them all. So, so you can reach everywhere. I mean, this is the definition of span, right? So these are the same. So you can hit everything, which is the same thing as onto. If something spans a codomain, then it's onto. It's onto that codomain. Okay. So it's onto. J is that it has an inverse. Oh, J and K both are about in. Oh, and L. So these are all just like. In this theorem, I forget what the proof of. I mean, I forget the proof that the transpose is invertible, but yeah. So okay, so this is basically an amazing theorem because it's just like, look at all of these different ways to say the exact same thing. Whoa. There's a lot of pollen in the air, man. All right, so first we need some notation. If the truth of a statement A implies that a statement J is true, A implies J. So A implies J. Why does J imply D? I really like these graphs, though. These proof graphs. Okay, that's so cool. Okay, so A invertible directly implies J, which is exists C such that CA equals I. And that implies D, which is that AX equal to 0 only has X equal to 0. And that directly implies C, A has N pivots, which implies B. So this is A, J, D, C, and B. And B is A is row equivalent to I. All right, let's do the proof. Okay, that first one was easy. If A is invertible, then J, then there's some C that is its inverse. Okay, next, J implies D, which is if there's a C, so C times A is the identity, then we only have the trivial solution. Let's duplicate this. $31. Oh, no. Okay, number 31 was oh. Oh. Um all right, so 31 is this. Suppose C times A is the identity matrix. Show that the equation AX equals 0 only has the trivial solution. What were the theorems of this section? Transpose theorems. The algebra. Thinking about matrix multiplication as a series of matrix vector multiplications, more algebra. Okay. I'm trying to think. How do we do this one? I remember doing it. I just so hold on. So if CA times X is equal, or if CA is equal to I, then I times X definitely only has the trivial solution. But why? But why? I want to know why. How ChatGPT proves this? I mean, like, I could say that if A, explain why A cannot have more columns than rows. So let's say C is m by n, and A is, I guess A would have to be n by n. Oh wait, this isn't going to work. C is n by m, and A is m by n. So then CA is n by n, and it's actually equal to the identity. If n were greater than m, then hold on, I'll be right back. Okay, so let's say that you have more columns than rows. Then the columns of A are dependent. They're linearly dependent, which means that you can make one of at least one of the columns 0, because you can make a linear combination of the other ones. From the other ones, I mean. Um, so if we were to do like a wait. Yeah, so my thing is that the second part, if it had more columns, then it would be have a linearly dependent column, at least one. So that means that you could effectively make that column 0. And if that column is 0, then the matrix multiplication of C times A would have a 0 column, right? So the matrix multiplication would need All right, let's get them. We can't spend all day. Yeah, okay, so this is how they do it. Okay, that's fine. That's perfectly acceptable. Okay, I'm good with that. All right, D implies C. What did we have with D implies C? That if it only has the trivial solution, then it has n pivots. So that's section 33. So suppose A is n by n, and we only have the trivial solution. Explain why it's row equivalent to I mean, if it's square and it has n pivot columns, then we know we can just back substitute and make it diagonal. And then at that point, you could just scale it. Okay, what's theorem? Yeah, wait, let's go through the theorems of 2.2 again. What are the theorems of 2.2? All right, 2.2 describes the definition of invertible, the fact that inverse is unique, the definition of, or the 2x2 formula for inverse, the definition of determinant, Okay, the uniqueness of solutions. Okay. And then the example. All right. Simplification rules. More simplification rules. What was this? Gauss theorem 6. The definition of elementary matrices, which is easy. All right. Theorem 7 is invertible if and only if row equivalent to the identity matrix. So suppose A invertible. All right, so this is the if and if proof. The first one is the obvious one. Then we have that. Then we know that. Oh yeah, and the cool thing about this is that every elementary row operation can be defined as a matrix. So that's nice. If an elementary row operation is performed, the resultant can be written as E times A. So then they generate this sequence of elementary row operations. So then the product of this yeah, I really liked that one. That one's cool. So which one are we doing now? We're trying to say D implies C, which is trivial solution implies pivot. All right, let's just do the review. We don't need to. Was it 33? So if you only have the trivial solution, because if you have another one that equals 0, then the columns are linearly independent or linearly dependent. If the columns are linearly dependent, then you're not going to have a pivot in that column. That's what I would say. The dimension of the kernel, I mean, this is beyond what we've done, but that's fine. All right, so that's how they do it. I mean, we haven't really learned that theorem yet, but I'm kind of chill with that. B implies A. Yeah, okay. That's chill. Next, A implies K. That's just the definition. K implies G. Which problem was it? 20. K implies G by 32. Oh, this is the other one of that? Okay. Okay, so if AD equals I, want to show for all B, AX equals B for some X. So what we can do is we can okay, you take AD equals I, then you multiply both sides by oh. Oh. I'm gonna get some sunglasses, dude. Stuff keeps flying in my eyes. It's so windy. Man, it's so windy today. All right. Okay. Ugh. What else is there? G. Okay. All right, let's look at this one. So it has 3 pivots, so it's invertible. Wow. The power of the invertible matrix theory lies in the connections it provides. Just so many concepts. All right. Okay, for invertible linear transformations, it's just applying the standard matrices, I guess. So this is, I think, a better picture of explaining why you might not have both ways. Like, if we're going from, like, let's say that this space is lower dimension than this space, then it could be that this inverse works, but this inverse wouldn't, because there are some points here that get collapsed down. Okay. All right. So let's I mean, these are all linearly dependent. This is not invertible. No freaking way. They're all um suppose that for a certain all right, statement G is what? Okay. So G is that AX equal to B, what is it called? Consistent for all B. Okay. And what can we say immediately is what it says? So let's say this is not true. And that means that there is some B with no solution for X. I'm pretty sure that that means I would just say that A doesn't span the dimension of B. And then let's do 3. Suppose A and B are n by n, and AB times x has a non-trivial solution. Well, then AB is not row equivalent to the identity matrix. Or equivalently, the columns or calls are dependent. I don't know. It's all the same stuff, I think. Let's see. What was the for the first one? Oh, they're obviously linearly dependent. Yeah, that was that example. Okay. It's not invertible. Oh, okay. See, yeah, but it all means the same stuff. Inconsistent for at least one B. Okay, so they just wanted us to say cause and event A, B not invertible. All right. Let's read through the problems and then we'll do some. All right, so read through the problems, then we'll do them. Okay, so these ones I think we can speed through a number of them without actually having to write them down. So with as few calculations as possible, figure out if they're invertible. This one is invertible because it's they're not multiples of each other. This one, so they're not dependent; they're independent. This one is not invertible because you multiply this thing by -3/2 or whatever. This one, if you take its transpose, you'll see that there's 3 pivots. So, and I'm pretty sure that if A is square and AT is invertible, then A implies A invertible. So that's that one. So 3 is invertible. This one's not because we have a linear dependence because there's a 0 column. This one, I don't know. I don't know about this one. All right, we did a few of them. Let's see. Here, we get the true false. We'll do the true false. All right, let's just do the true false now so that we don't have to keep switching back and forth. All right, all the matrices are n by n. Each part of the exercise is an implication. I'm pretty sure that's true. So 11, let me set 1 down just because. So this is what, 2.3 exercises. 11 is true. A is row equivalent to I. 12, if there's an n by n d that AD equals I, then there's also an n by n c such as CA equals I. Yeah, that's true. 13. And we can actually, if we have AD equals I, then we multiply by D inverse. And we get AD D inverse equals I D inverse, which is equal to A is equal to D inverse. I don't know. If they're n by n, then we're good. So that one was true. If the columns of A span Rn, if A, which is n by n, spans Rn, I'm pretty sure that's true, because if it's n by n, then you have n pivots. 14. If the columns of A are linearly independent, then the columns of A span Rn. See, that one, if it wasn't for the fact that we know that A is n by n, wouldn't be true, but it is true. If A is n by n, then the equation x equals b has that's just false. That's just false. Because we don't know. The rank of it could be low. There could be a big kernel. If the equation has at least one solution for each b, then the solution is unique for each b. So that's another one where if you assume it's n by n, then it should be true. I think 17 also true. If you have ax equals 0 as a non-trivial solution, then yeah, you're gonna not have some pivots. '18's false. I think it's because it's crucially that they don't say onto. If it said onto, then it would be different. If AT is nonverbal, then A is nonverbal. That's true. If there's a B and it's just a inconsistent, then it's not 1-to-1. Wow, they really mess with you, because I think that's also going to be true. Just because of the A is n by n. If it doesn't span the codomain and it's square, then it's got to have a dependent column. So this one is true, I think. All right, let's look at the answers. I'm kind of expecting ChatGPT to like, bro, the sunglasses are hilarious. True, 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 false, true, true, false, true, true. Okay, cool. So I was right. I got them all right. When is a square upper triangular matrix invertible? When it has a pivot, when it has n pivots, I would say. Oh wait, it's m by n though. Oh, but okay. When is a square upper triangular matrix invertible? I'm guessing when pivots all on, or like when all diagonal elements. So I think I think if any element on the diagonal is not, if any element on the diagonal is a 0, then it's not going to be invertible. Let's see. If they're all, oh, it's invertible. If they're all non-zero. Yeah, that's what I said. Okay, cool. This is the same. This is the same answer. Can a square matrix with two identical columns be invertible? No. If square and cols are dependent, then it's not going to have n pivots. So it's not gonna be invertible. Come on. Is it possible for a 5 by 5 matrix to be invertible when its columns do not span R5? No, fuck no. Come on. No. If its columns don't span R5, oh man, I'm sneezing like crazy today. Because it's much more helpful to think of these arguments in terms of dimension. I don't know why I'm trying to think of them in something not dimension. Okay, if the span, let's say the span is R4, then there's no way to go from R4 to R5. That's my argument. No way to go to span R4 from, or R5 from R4. So that's how I would explain it. Just think about it in terms of dimensions. Okay. If A is invertible, then the columns of A inverse are linearly independent. Yes, because if A is invertible, then A inverse is invertible. And if A inverse is invertible, then it has to have independent columns. So 25 is yes. 26, so it spans the codomain. Is it possible that for some V has more than one solution? Okay, so let's think about that in terms of dimension. if you can get to the same place in two different ways, meaning two different solutions for x, then there's got to be a linear dependence in the columns, I believe. So my answer is no, because if we have two different x such that cx equal to v, then we must have dependent calls. Right, exactly, because there. Oh, that's how I should think about it. I forget to think about that. It's like because that gives you the path. So if for 26, if we had ax1 equal to b, ax2 equal to b, x1 not equal to x2, but a times x1 minus x2 is going to be equal to 0, but b minus b is equal to 0. Wait, actually, what's an example? A small example for when wait, okay, a equals 1, 1, 2, 2, x1 is equal to 3, 6. So if we have x1 is equal to 3, 0. Oh yeah, definitely. Okay, cool. Three, 6. So okay. So wait, so 3, 0 goes to 3, 6, and 0, 3 goes to. So okay. 27. If D linearly independent and it's square, what can we say about solutions? They're unique and they exist for all B. I mean, because D is row equivalent to the identity matrix. And for all B, I of B is equal to B. So we can just get any solution. If n by n matrices E and F have the property that EF equals I, then E and F commute. Explain why. So we have E, so this is 28. E times F equals I. I think if we multiply by E, what? All right, so we have EF equals equal to I. If we did, so we don't know that they're invertible, right? So, but if we multiply, so if we get EFE is equal to IE, then this is still EFE is equal to E. But that means that EF is equal to FE. Okay, that's obvious. 29. If Gx equal to Y is more than one solution for some Y in Rn, can the columns of G span Rn? Yeah, of course they can. What? Why wouldn't they be able to do that? Of course they can. Wait. No, it didn't say anything about that. Okay. Yeah, it didn't say anything about G. Wow, these are boring, man. 30 hx equals c is inconsistent. Um, ooh, this one's good. I think it's still possible that I'm pretty sure it's still possible that it doesn't span the codomain, but it still has non-trivial zeros. Okay. Wait. What? Yeah, okay. Yeah, exactly. This is how you should always think about these, I think. Is you just put the identity and then you add a 0 row or column. H is equal to 1 0 0 1 0 0. And then G is equal to 1 0 0 0 1 0. Okay. The columns have to be dependent, right? If it's n by n and it can't be reduced, then there's a dependency. Right, yeah. I guess a pivot's argument makes sense. If L is n by n and has the trivial solutions, so this one doesn't say only has the trivial solutions. So I'm thinking about a case where we have an n by n. No, no, you can't conclude that they span. Just because it has a, I mean, all of them have it. Verify the boxing. I don't know. Explain why the columns of a squared span Rn whenever the. Ooh, that one seems cool. If so, wait, but we don't even know if a is or wait, we do know a is square, right? Because if a wasn't square, then you'd get m by n times m by n. So a is square. If you take a matrix power, then it's square. So I wonder what they say, because it's got to be square, and a is linearly independent. So since it's linearly independent, it's invertible. So we can invert it. So we're gonna get a times a inverse, or a inverse times a is equal to a inverse b. So this cancels out, and we get a is equal to a inverse b. Oh wait, no, ax is equal to a inverse b. Wait, do it again. Then we get a inverse ax is equal to. Oh, wait. A inverse times a inverse. So it's going to be a inverse squared times b. All right. I think I showed the proof, but I want to know what it is. Yeah, independent means kernels just the zero. Yeah, a is invertible. Surjectivity of a squared. To show the columns span Rn, pick an arbitrary b that y equals a times x, then ay equals b. Since a is invertible, then there's a unique solution to ax. Okay. Yeah, okay, that's what I did. This is exactly what I did. I just didn't make y. All right. Show that if AB is invertible, so is A. One 6B. Yeah, that's what I was thinking. Okay, you can't use that. Um. Well, this one's good. Okay. Let's see what else we got here. Um. if AB is invertible, oh yeah, so I got to the associativity part, but I didn't think of rewriting it as AD. Okay. Yeah, that's okay. So that's what you do. So you have AB times C is equal to I. This is equal to A times BC is equal to I. Then D is equal to B times C, so AD equals I. So I so A is equal to D inverse and D is equal to A inverse. I don't know. I think that's true. This one maybe a little bit harder. No, I think it's fine because you just do it the other way. CAB is equal to A, and so this is 36. C times AB is equal to I. Then CA times B, but by associativity is equal to I. So then, DB is equal to I. So then B is equal to D inverse, and D inverse, or D is equal to B inverse, something like that. Okay. How many more of these do we want to do? A is n by n. Well, because it's not one-to-one, you're going to have a dependence because you're going to take two vectors that go to the same place. You take their subtraction, you apply the transformation. So that means you have a non-trivial solution to the homogeneous equation. So that means that you have a dependence. That means you don't have n pivots. That means that you're not going to span the codomain. These are boring, man. If A is n by n and the matrix is 1-to-1, it's invertible. It's literally direct application of the thing. If it's square and 1-to-1, then it's invertible and you get everything. If A is n by n, What am I trying to say? I'm trying to say that let's say you hit everything else, you hit everything in Rn, and you're trying to say that it's not unique. If it's not unique, then you're trying to get space from space you don't have. You can't use your dimension like that. Essentially. Yeah, it's a good question. Why am I using ChatGPT? I probably shouldn't use it as much as I am. That being said, for this section in particular, I mean, it's more so I come up with a solution and then I ask. And it's more so just to make sure that mine is correct. But I kind of agree with you. I mean, for all of these past ones, I really haven't really been using it. Look, if it's n by n and you can't get to 0 by any other means than through 0, without using the invertible matrix theorem, why must it span? Well, it's n by n, and it only has the trivial solution. So we have n pivots, then the columns are independent, and since we have n independent columns, we must span Rn. That's my proof. I think that's right. Nah, no, it's boring. One-to-one and onto. If it's invertible, then it's one-to-one and onto because it's invertible and then it's got n pivots, so it's row equivalent to the identity. If it's row equivalent to the identity, obviously it's one-to-one. And it's onto because for any b, I times b equals b, so then b is input. So it's one-to-one and onto. Then given it by using one or more theorems, I don't know. It's equations 1 and 2. Oh, wait. Were they talking about? What are equations 1 and 2? These. Okay. Let T be a linear transformation that maps R into Rn. Show that the inverse exists and maps Rn onto Rn. Wait. Oh. Okay. Yeah. The hard part for me about this stuff is that you read the word onto and you just forget that onto actually has a precise meaning. So, okay, so we span the codomain. We also could immediately say that if it's going from Rn onto Rn, then the standard matrix of the transformation is going to have n pivots. So it must be invertible. And if it's invertible, then we have like, what is it? S of t of x is equal to x, and what's the other one? T of s of x is equal to, right. Okay, but these are not the same Rn. So then we also have T of S of X is equal to X. So it's going to be onto, because the inverse exists. And for all X in the codomain, which is, I guess, the same as the domain. I know if you know the inverse exists, then it has to be onto itself. Oh, but they're not saying that. They're saying T inverse exists and is onto. So S from V to U, if you're thinking about vector spaces, is onto. I mean, if the linear transformation is invertible and the codomain and the domain have the same dimension, then the inverse must span T, or yeah. All right, so is this in a special character, or is this literally just a space? So my solution is, since T standard matrix of T is square, Rn to Rn, and onto, then the standard matrix A is square and has n pivots, therefore it's invertible. Since the domain and codomain have the same dimension, square, then the inverse T minus 1 is also sending Rn to Rn and is invertible and onto. T minus 1 is 1 to 1 for the same reason that its inverse exists let's see. I want to see how it answers it, but I think it's, here's a structured write-up. T is onto Rn, so its rank is n. T is multiplication by a standard matrix. Surjectivity means the columns of A span Rn. Okay, that's the same thing. Yeah. An n by n matrix with rank n has n pivots. So by the invertible, its inverse exists. Okay, so we got to that part. Now T inverse exists Since A inverse exists, the inverse transformation T inverse is given by its matrix. Yeah, so that's fine. So we know that, but A inverse itself is full rank, so its columns span Rn, meaning T inverse is also onto. The inverse of a function is always 1-to-1. Okay. Suppose T and U are linear transformations from Rn to Rn. Okay. So 45 seems like a good one. I like 45. So let's say we have TU from Rn to Rn. And for all x, T times Ux is equal to x. And then the question is U T of x equal to x for all x? Why or why not? So what we can do is, because of the associativity of matrix and vector multiplication, we can say T times U is equal to x for all x. So then T times U is equal to the identity in a way. It's not the identity. I mean, it's the identity function, really. Because these are transformations we're talking about, and it's not specifically. Well, I guess it is. Because since it's from Rn to Rn, then it has a standard matrix. So we could just associate T and U with their standard matrices. And so that means that T is equal to U inverse. I wish we were doing more problems where it was rectangular. Where like only the right inverse exists or something like that. But I'm pretty sure this is true because okay. I think it's again just about the rank of the because T, hold on. Right. Oh, this is a good way to put it. T composed with U, T after U, it or I mean, yeah, of x for all x is equal to x for all x implies that U is surjective and T is injective. Oh, wait. Hold on. No, just T after U. U is injective. Yeah, U is injective. And T is surjective. But if we're going from Rn, like, if you're going from Rn to Rn, and you have something surjective, it's also going to be injective. Yeah, exactly. The dimension of the kernel is 0, therefore it's onto as well. Yeah, so you always just use this rank nullity theorem or whatever. That's the way to do it, man. It simplifies so many of the proofs. Yeah, a left inverse on Rn is also a right inverse. Right, and this follows immediately from this rank nullity thing, I think. Okay. That's chill as hell, brother. That's chill as hell. Okay, what else do we need to do here? Oh my gosh, Firefox, please stop breaking my balls. Suppose a linear transformation Rn to Rn has the property that Tu is equal to Tv for some pair of distinct vectors. Can T map Rn onto? No, bro. Not at all. You gotta be getting that dimension from somewhere. And that dimension is coming from your codomain. This is obvious. By the rank nullity theorem. Right, exactly. You do this. So the kernel of T contains a non-zero vector, so it's not 1-to-1. So then by the rank nullity theorem, we have there's some dimension from the kernel that you're pulling from the rank. Yeah, I really I like those proofs way more. Okay, so we did all the exercises in only an hour and 40 minutes. So this is pretty quick. I mean, I don't know how many more we need to do. I think we're good. Okay, so I'm going to end this one. Then we're going to do linear differential equations. But I need to do the actual, like, online homework. All right. Time to end it. See ya.